Having seen now Euclid's algorithm, we want to arrive at the fundamental theorem of arithmetic. And it says that every number can be written as a unique prime number factorization. So for example, if I have 12, it can be uniquely written as a product of prime numbers, 2 times 2 times 3. Or if you like, 2 to the second times 3. So this is the only way you can write 12 as a prime factorization. Of course, it's regarding order of the numbers. So it means that if you have prime factorization, there must be 2 2's and 1 3. So in this way, it's unique. So that's called the fundamental theorem of arithmetic. But to arrive at that, we need some theorems and results to prove that. And Euclid's algorithm will play a part there also. So let us start with the theorem we need. And it says that given integers a and b, so we have a and b, we can always find integers x and y such that the greatest common divisor of a and b can be written as x times a plus y times b. So that's the result of this theorem, what this theorem claims. And this is true and can be proven. And in the book I have proven it, but I will not prove it now. Let me just take an example. So let's say we have the greatest common divisor of 19 and 7. So a and b is 19 and 7. Then we can find x and y. And those are, we can write it, the greatest common divisor we can write like this. 3 times 19 plus minus 8 times 7. Okay, so we can find numbers x and y. In this case, those numbers are 3 and minus 8. So this just illustrates how it works. This is the theorem that we can always find numbers x and y such that this holds, that the greatest common divisor can be written as 3 times one number and y times the other number, or x times one number or y times the other number, and there exists numbers x and y. And by using that theorem, you can prove the following theorem. That if you assume that p is a prime number, and that a and b are integers, are natural numbers, so they are positive integers or 0, then the following thing holds. If p divides the product ab, so we can write the parentheses here, but it divides the product ab, then it follows that p must divide a, or p must divide b. So if you have a product of two integers or natural numbers, and if you have a prime number that we know divides the product of those, then we know that the p must divide either the first one or the second one, or possibly also both. So we must have that it divides at least one of them. So let's take an example of showing this. Let's take 14 and 10. So a is 14, b is 10. And let's take our prime number as 7. Then 7 divides the product AB, because what is the product? That's 14 times 10, that's 140. So we have that 7 divides 140. So it divides the product 14 times 10. But then according to this theorem here, we know that 7 must divide 14, or 7 must divide 10. So at least one of these must be true. We can see directly this is not true. So this must be true. And this is true, since 7 does indeed divide 14. So that's an example of this theorem here. And the proof of that is also given in the book. I will not do it here. And then we finally can prove now the fundamental theorem of arithmetic. So it says that if all natural numbers greater than 1 can always be expressed as a product of prime numbers. And this product is unique if you disregard the order of the numbers here, but only which prime numbers are included in this. Then this product is unique. So you can always write it like a product of prime numbers, and the prime numbers are unique up to order. So that's the result of the fundamental theorem of arithmetic. So it's very important and central theorem of number theory. For example, if you have 60, you can write it as 2 times 2 times 3 times 5. So it's always possible to write it as a product of prime numbers. And this is the only way to write it as a product of prime numbers if we don't care about the order. For example, we could put 3 first, of course, but the point here is that we have 2 2s, 1 3, and 1 5. That's the only way we can write it as a product of prime numbers. And we can also write it like this, of course. Or just taking another example. Then the prime number factorization is this. Of course, it can take a while to arrive at this result, but it's always possible to find the unique prime factorization. There is one, and it can be found. Okay, so let's now make a sketch of the proof. So we'll make a sketch of the proof. Let's then take a number, natural number n, that we know that is bigger than 1. If n is a prime number, then we are finished, because we consider a prime number to be a product of prime numbers, trivially. Just having 1, that's a trivial product of prime numbers. And if it's not a prime number, then we know that we can write it as a product of 2 natural numbers here, smaller than n and greater than 1. And now we can do the same reasoning, like if a and b both are prime numbers, then we are finished. So there is nothing to show. So we can assume here that at least one of them should be a prime number, a non-prime number, so that is a composite number. Okay, so let's say that one of these are not prime numbers. Let's say this is a composite number. Then we can, of course, write this. That's the meaning of that. We can write this as a product of 2 numbers. Okay, so then we can divide it up like this. And now if these are prime numbers, then we're finished, because then all 3 are prime numbers. If it's not, if one of these are composite, let's say this one, then we just continue. At some point we must end up here at prime numbers, because these numbers become smaller and smaller. So let's take an example of this. Let's say we have 2340. This we can write as 18 times 130. There are other ways to write this a multiplication of 2 factors, but this is one way. Now both of these are not prime numbers, so let's continue to write them up as a product of 2 numbers. These are composite. So we can write this as 2 times 9, for example. And this we can write as 13 times 10. Here's a prime number now. So that then we are finished in this branch. This one is not, so we can write it as 3 times 3. 13 is a prime number. 10 is not, so we can continue with that one. 2 times 5. And now all are prime numbers here. So then we find that our prime number factorization is 2 times 3 times 3 times 13 times 2 times 5. Or we have two of these, 1, 5, and then 13. So this we always do. So this is a sketch of the proof. Then you should, of course, you should prove it. You should do it more carefully here and not just sketch it. But this is the into2 idea behind that you can do it. So this proves one part, half of the theorem, that you can always write a number as a product of prime numbers. What now remains is to show that this product here is unique. So there is no other way of writing this number as a prime number here, product, disregarding order, of course. So we couldn't write it as a 7 times. So there is no other prime number factorization we can find. And that we want to prove now. To show it's unique, let's take our number here now. Let's say we have found two different prime number factorizations. So all these numbers here, Q1, Q2, Q3, and so on, they are prime numbers. And then we have another prime we assume that we have another one, since we now want to show that it's unique. So we want to end up to show that actually these must be the same. But let's assume that we have two different. Let's see where that leads us. Okay, then we used another theorem we saw earlier. And for example, on the left hand side now we see that P1 divides the left hand side. So the P1 divides the left hand side. And that, so it divides this long product here. Of course, since P1 is included there, it must divide. And then that means since these two sides are the same number, it must also divide the right hand side. So it means that it must also divide this product. Then we can use a previous result we had. We had this theorem. You saw that if P divides a product, a prime number divides a product, it must divide one of these two numbers. And this can be regarded as a product of two numbers. Here is one number, and here is the rest of the number. So if you take this, multiply this together, this will give us a second number. So this is A, and this is B. So we know now, according to that theorem, that P1 must either divide Q1, or it must divide this product of the remaining ones, Q2, Qm. Now we have assumed that Q1 is a prime number. So if this is the case, if P1 divides Q1, then we must have that P1 is equal to Q1. Okay, but if this is not the case, then this must be true. Then we have the same situation as we had before here now. Then we can continue to use the theorem that P1 must divide either Q2 or P1 must divide the remaining ones, the product of the remaining ones. Continue this way, at some point P1 must divide some of these prime numbers here. So P1 must be equal to some of those prime numbers. Let's call that whatever, QR. So P1 must be equal to some of these prime numbers here. Okay. And then, what can we do then? Let's say it's equal to the third one, for example. Then P1 is here and P1 is here. Then we can divide on both sides. Then we have remaining P2. After you have divided, we have P3, PK. And then we have all of these, Q1, Q2. But now we have divided away Q3, so now we have Q4 and Qm. But now we can repeat the whole argument. Now we do the same thing again with P2. Then P2 must be same as some of these here. So if you continue this fashion until we have divided away all of them, then we must end up with the 1. And here
we must up with the remaining number of prime numbers. So let's say that that's Q5 and Q7, for example, Q11, whatever. First of all, we cannot have a product of prime numbers equal to 1. So we see here that now this cannot happen. So it must be the same number of prime numbers on both sides. So we must end up with 1 on this side also. So we will not have like this situation where we will have a 1. So you have the same number of prime numbers on both sides. And all of them are same because all of them can be paired. Q1 was the same as Q3. P2 was the same as some of here. So you see that all the prime numbers on both sides are the same. And thereby we are proven that these are the same prime factorizations up to order. So it's unique. And again, this was a sketch. You can do it even more carefully, of course. So thereby we have proven our theorem, that the fundamental theorem of arithmetic, that we can always write as a product of prime numbers and that this product is unique up to order. And we will end this on prime numbers by proving now that there are infinitely many prime numbers. So that means that we take 2, 3, 5, 7, 11, 13. This will continue indefinitely. Okay, so now we want to prove that. And then we want to use a proof by contradiction. So we want to assume that the opposite is true. So let's assume that the opposite of this is true. And that means there's only finitely many prime numbers. And then we can list them. So if there are only finitely many, that means that there must be a list of them. P1, P2, P3, up to some number Pn. So we have assumed that it's opposite. Okay, now let's define a number. If we now assume these are only prime numbers, let's define a number q, as we write as the product of all these. And then we add 1. Okay. Then we see that none of these prime numbers, we cannot write this q here now as a product of these prime numbers. And why is that? According to the fundamental theorem of arithmetic, we should be able to write now q as a product of prime numbers. So for example, we should be able to write pu and maybe 2 of those and p3, 4 of those, or whatever. But that's not possible, because if we will find such a product, let's say that that product contains, for example, p1. So if you have a product here, it contains p1, and it could be, for example, to the third or to the first, it doesn't matter. And then some other here. Now I'm making a sketch again, but of course this can be done more carefully. But let's say this product, then we see that P1 must divide Q. But if we look at this, we see that P1 cannot divide Q here, because if we try a division of P1 with Q here, we will always get the remainder, or we get the remainder of 1. You say no matter which of these prime numbers we try to divide Q with, we always get the remainder of 1. So none of these prime numbers can divide Q. So that means that we cannot find a product here of prime numbers to write Q. But that should be possible according to the fundamental theorem of arithmetic. So we see here that we arrive at a contradiction. So if we assume that there are finitely many and list them like this, then we form this number. Then we see that none of the prime numbers divides this number here. But that shouldn't happen, because we know that we can always write every number, including this one, as a product of prime numbers. And if you have the product of prime numbers, some of them should divide Q, but according to this, they don't. So we have arrived at a contradiction. And that means that our assumption that there are finitely many must be wrong. And that means that there are infinitely many.